Okay, so we're going to do a quick physical properties review, and that's going to be our last thing for today's lecture. So I know you guys covered electronegativity in the last class, but could you give me a definition for electronegativity? So electronegativity is the ability of a bonded atom to attract shared electrons. So this can give us a lot of insight into what type of forces are holding two atoms together. Okay, so what I have here are the electronegativity values from the periodic table. I got this at ptable.com. And these are the 6 atoms that you see over and over again in biomolecules: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. So if the electronegativity difference between two atoms is less than 0.5, so for example, if we have a carbon bonded to a hydrogen, that's less than 0.5, that's going to equate to a non-polar covalent bond. So what that means is the two electrons, the shared electrons between this carbon and hydrogen, are going to spend roughly equal time around both atoms. They're going to spend a little bit more time around the carbon, but for all intents and purposes, this is a non-polar bond. Okay, so if that electronegativity difference is between 0.5 and 1.9, something like we would have with oxygen and hydrogen, that's going to equate to a polar covalent bond. So that means when we have an oxygen and a hydrogen bonded together, the electrons are going to spend so much more time around this oxygen than the hydrogen that we're going to develop what we call a dipole, where we have a partial negative charge on the oxygen and a partial positive charge on the hydrogen. And that little symbol I drew is the lowercase Greek letter delta. So what if we have an electronegativity difference greater than 1.9? So we can't have that with any of these atoms here, any of these 6 common atoms we see in biomolecules. That's going to generally require an interaction between a metal and a nonmetal, so something like sodium chloride. So sodium has an electronegativity of 0.93. Chlorine has an electronegativity of 3.16. So that electronegativity difference is so big, it's bigger than 1.9, so they're not going to share valence electrons. Chlorine is just going to take sodium's 1 valence electron, and that's going to give us an ionic bond or an electrostatic interaction. Okay, so speaking of ionic bonds or electrostatic interactions, let's talk a little bit about bonding and intermolecular forces. So I don't want you to memorize these numbers on the right for bond strength. Just know that the bigger the number, the stronger the interaction it is, the more energy it would take to break that interaction apart. Okay, so we already talked about covalent and ionic interactions in the last slide. Now we're going to talk about van der Waals forces. So van der Waals forces are weak, transient, distant dependent forces. And for this class, that's going to include hydrogen bonds, dipole-dipole interactions, and London dispersion forces. So you guys covered hydrogen bonding in the last class, but just for a quick refresher, that's going to be an interaction between a nitrogen, oxygen, or fluorine atom and a hydrogen atom that is covalently bonded to a different nitrogen, oxygen, or fluorine atom. So we're going to refer to the side with the covalently bonded hydrogen as the hydrogen bond donor. We're going to refer to the side without the hydrogen as the hydrogen bond acceptor. And we're going to show this hydrogen bond or really any weak interaction with a dotted line. So our next one is a dipole-dipole interaction, which I don't think you talked about in the last class, but this is another noncovalent interaction that involves the attraction of two opposite dipoles. So remember from the last slide, we have enough of an electronegativity difference between carbon and oxygen that these 4 electrons that make up this double bond are going to spend more time around the oxygen than the carbon, and that's going to result in a partial negative charge on the oxygen and a partial positive charge on the carbon. And same thing with this neighboring carbonyl right here. We're going to have a partial positive on this carbon and a partial negative on this oxygen. And this partial negative from the first molecule is going to be able to interact with the partial positive on the second molecule. And as you can see from the numbers on the right, on average, that's only about half as strong as a hydrogen bond. And so our last one here is the London dispersion force. That is the weakest of these intermolecular forces, and that results from the continuous movement of electrons forming temporary dipoles. Okay, so I'm going to do a little demonstration using a helium atom. So helium is going to have proton, 2 protons, 2 neutrons in the nucleus, and 2 electrons orbiting the nucleus. But those electrons aren't in a fixed location. They're continuously moving. And at any one snapshot in time, we could have the 2 electrons fairly near each other. So we could move this electron up here. And if we just freeze time, and draw a line right through the middle, we're not going to have an equal distribution of charges. And so this is what we call an instantaneous dipole. It only lasts for just an instant, and then it's gone. But let's say there's another helium atom in close proximity where the same phenomenon is occurring. So for just a split second, we're going to have a very weak interaction between these 2 instantaneous dipoles. And that weak interaction is what we call a London force. So why is such a weak force so important to organic chemistry? Well, the reason is because it's additive and it helps determine the physical properties. So let's take a look at these 2 molecules right here. So this molecule on the left is normal pentane, and the one on the right is neopentane. And they both have the same molecular formula. They both have 5 carbons and 12 hydrogens, but they have radically different boiling points. So normal pentane has a boiling point of 36.1 degrees Celsius. So that means at room temperature, normal pentane is going to be a liquid. Neopentane, however, has a boiling point of only 9.5 degrees. So that means at room temperature, it's going to exist as a gas. And the reason is normal pentane has a much larger surface area than neopentane. So there's more places that 2 pentane molecules could come into contact with each other than 2 neopentane molecules. And the more places that you come in contact with other molecules, the more shared surface area you have, the more places you can make these London interactions. And these London interactions, even though they're very weak, they're additive. So they add up and it requires more energy to break them apart. So it's going to increase the molecule's melting points and boiling points. So the big takeaway, what you need to remember for the rest of this class, the greater the surface area, the more London forces it can make, the higher the melting point and boiling points will be. Okay, similar to melting and boiling points, these intermolecular forces can affect solubility as well. And this is a biochemistry class, so for the most part, we're going to be concerned with aqueous solutions. So we're concerned with water solubility. So I'm sure you heard in your last class the phrase like dissolves like. So when you're trying to determine if a particle can dissolve in water, ask yourself, is the particle about the same size as a water molecule? And can it interact with the water molecule through non-covalent interactions? So lots of times in this class, I'm going to ask you to compare the water solubility of different molecules. So for molecules of roughly the same size, you need to ask yourself which ones can make the strongest interaction with water. And that's going to be the one that is most likely the most soluble in water. So let's try an example. So here I have 3 molecules that are roughly the same molecular weight. I want you to go ahead and pause the video and see if you can rank these molecules in order of water solubility. Okay, so I pulled up our table of non-covalent interactions as a reference here. And let's look at each of these molecules and figure out what the strongest interaction each one of them can make with water. Okay, so the strongest non-covalent interaction is the ionic bond or electrostatic interaction, but that is going to require 2 ions to interact. We don't have any ions here, so we can go ahead and move on to the next one. So what about hydrogen bonds? So hydrogen bonds, we need a hydrogen bond donor where we have a nitrogen, oxygen, or fluorine attached to a hydrogen. And we're going to need an acceptor, which is going to be another oxygen, nitrogen, or fluorine atom. Okay, so let's start on the right over here with our ether. So we don't have a hydrogen attached to an oxygen, nitrogen, or fluorine. So this molecule cannot act as a hydrogen bond donor. But since it does have an oxygen, it can act as a hydrogen bond acceptor, and that is going to be the most favorable way this molecule can interact with water. Okay, now let's take a look at our alcohol in the middle. So our alcohol has a hydrogen attached to an oxygen, so it can act as both a hydrogen bond donor and a hydrogen bond acceptor. Okay, so what about our last one? What about this alkane on the end? Well, it definitely can't hydrogen bond with water because it doesn't have any oxygens, nitrogens, or fluorines. It can't form dipole-dipole interactions because it doesn't have any polar covalent bonds. So the strongest interaction it's going to be able to make with water would be London dispersion forces. And in fact, as we're going to see later in the semester when we talk about the hydrophobic effect, the water molecules are going to arrange themselves to maximize the number of hydrogen bonds they can make with themselves and minimize the surface area they have in common with the alkane. So if you received a question like this on an exam, it would be safe to assume that the alcohol will have the highest water solubility because it can form the greatest number of hydrogen bonds with water, followed by the ether, and in a distant third will be our alkane, which is going to have a hard time interacting with water at all.